Hi, I am Ankita, and I'm here to present our work studying self-supervised speech models. This is a joint work with Chung-Ming Chien and Karen from TTIC. Let's start with a quick introduction to self-supervised models and the motivation for our study. A successful self-supervised speech model is an answer to whether there is a way to put a ton of unlabeled speech data to good use. A self-supervised approach relies on artificially generating labels from raw audio files. For example, masking the input and recovering the clean audio. The hope is that the pre-trained network learns meaningful representations that we can effectively use for supervised downstream tasks with limited additional parameters. Self-supervised speech models, also abbreviated as S3Ms hereafter, have been an active area of research for almost a decade. However, we started seeing phenomenal success around 2020, and since then, a plethora of new models have been developed. These recent models show remarkable capabilities on downstream tasks and have also provided an effective backbone for challenging tasks such as unsupervised speech recognition and scaling up multilingual speech models. However, we have made slower progress in developing a fundamental understanding of what is it that S3Ms learn during pre-training. That's where our work comes in. Our goal is to develop a better understanding of these models using a framework that can be easily scaled up to study multiple S3Ms. To that end, we employ lightweight tools to interpret the knowledge encoded in S3Ms. With that goal in mind, I'll now introduce our analysis framework. This is a typical schematic for current day S3Ms. Raw audio is processed through some CNN layers to get frame-level features. A frame is typically around 20 milliseconds. These local features are then processed through some transformer layers. We study frame level and word level representations extracted at each layer, then we evaluate the representations in multiple ways, falling into two categories. One uses training-free tasks and other uses CCA. I'll return to our task-based study when I discuss our findings. For CCA, once we have the pooled word representations from an S3M layer, we use CCA to compare S3M representations with an external variable. For instance, for every X, we have a corresponding word identity that can be converted to a one-hot vector. CCA measures similarity between X and Y as a correlation between their linear projections. The optimal solution projects X and Y such that the correlation between the projected data is maximized. V and W are learned, and CCA has a closed-form solution which is typically quick to compute. Comparing S3M representations with word identity should tell us how well the intermediate representations encode word identifying information. In addition, we compare the word level representations with different word vectors to measure word level pronunciation, semantics, and syntax. Today I'll discuss our findings from the first three experiments. For word pronunciation, we use word embeddings from Shi et al. Acoustically grounded word embeddings encode a written word into a representation that captures how that word sounds. So similar sounding words are placed closer together. For semantic attributes, we use the word embeddings introduced by Svetko et al. These 41-dimensional embeddings are curated from word sense annotation, and each dimension corresponds to an attribute. For instance, family has a high value for group attribute, and mix has a high value for change attribute. So that was CCA. Next, I'll introduce a subset of S3Ms we analyze in our work. And today we'll discuss results specific to these models. This is the same schematic we saw before. The pre-training loss is a function of the final contextualized representations, and different models differ in the target they use for this loss function, as well as the form of the pre-training objective. Wave2Vec 2.0 is trained to recover a quantized version of these local features with a contrastive loss. Hubert has the same model architecture as Wave2Vec 2.0, but is trained iteratively with a BERT-style predictive loss. It uses a discretized version of an intermediate layer as a target. And then we have visually grounded Hubert. We use the speech branch for our analysis. VG Hubert is trained on images paired with audio captions with a margin contrastive loss, which uses representations from the image encoder as the target. Great, so now we are well positioned to look at the results. First, let's look at CCA similarity between S3Ms and linguistic features. The x-axis shows the transformer layer number, and most models have two versions, a smaller one with 12 layers and a larger one with 24. The y-axis shows CCA similarity between the word segment representations and the corresponding property vector, which is word pronunciation in this case. For Wave2Vec 2.0, we see that the intermediate layers are most correlated to the pronunciation content, and then there is a drastic drop towards the end. Semantic content also follows a similar trend with a drastic drop at the end. This should not be too surprising given that the pre-training objective reconstructs local features. So naturally the final layers would mimic the behavior of the bottom layers. For Hubert, the most linguistic layers are different from Wave2Vec 2.0, but a more striking difference is that there is little to no drop for the last few layers. This aligns with our understanding of the pre-training objective, which no longer reconstructs the local features, but recovers an intermediate layer. Analysis from Hubert paper suggests that the intermediate units are phone-like units. So naturally, if Hubert is trained to recover phone-like units, the final layer should be learning phonetic content, which explains this high correlation with word pronunciation. But for semantic content, we do see a drop for the final Hubert layers. This further confirms that the Hubert pre-training objective is more phonetic than semantic. Additionally, we consistently see that this plateau of best layers is much narrower for semantic content than for the word pronunciation content, both for Hubert as well as Wave2Vec 2.0. This suggests that the deeper linguistic property, which is word meaning in this case, is better encoded in deeper layers. For visually grounded Hubert, we do not see a significant drop as we saw for Hubert. This behavior suggests that the meaningful semantic content is retained better with the grounding signals provided by the image encoder. So far, we saw results analyzing mean pool word representations. For the next part, we represent the word segment using only a subset of frames or even just a single frame from the word segment. Here we are looking at CCA between mean pool word representations and word identity for Wave2Vec 2.0. So we are measuring how word identifying content is distributed across layers. Next we'll see how different pooling strategies impact these similarity scores. Instead of mean pooling, if we were to represent words using only the last frame or the last quarter of the segment, we see that the CCA similarity drops drastically across all layers. Same is true when using only the first part of the segment. But if we were to represent the word using the frames in the center of the segment or even just a single central frame, the similarity values almost match the ones from mean pool representations. This strongly suggests that the central frames encode the most word identifying content and also raises the question of whether mean pooling is indeed an optimal strategy. So that brings us to the last set of findings. And as promised, this is where I'll discuss our task-based studies, but at a very high level, touching just the key points. The first task evaluates whether two spoken word segments belong to the same word. Here we compare mean pooling with an approach that finds optimal frame level alignment between two word segments. We find that some S3Ms are more robust to mean pooling than others. The second task is word segmentation. In the previous plots, we saw how edge frames had little to no similarity with word identity. So we evaluate frame level representations for unsupervised word segmentation using a simple algorithm based on peak detection. We find that the STM representations are surprisingly effective at detecting word boundaries. Lastly, we evaluate spoken sentence representations on a sentence level similarity task and find that the mean pool sentence representations encode non-trivial semantic content surpassing the baselines. Additionally, we find that the task-agnostic CCA layer-wise trends agree with the layer-wise trends from all these task-based studies. To summarize, I presented our lightweight analysis tools used to analyze 10 S3Ms in our paper with a focus on studying word-level knowledge encoded in self-supervised speech models. It is still common for S3Ms to be fine-tuned for downstream tasks, so we hope that our findings can assist in making informed decision choices when designing task-specific adaptation strategies. Finally, in the last couple of years, the community has started making significant efforts to develop a fundamental understanding of these models. Please refer to our paper for a detailed discussion of all the relevant prior work that I couldn't do justice to in this short presentation. Thank you all for your attention. I'm very happy to chat at our in-person sessions at ACL. Thank you.